Part 3. Considerations on the universe as a whole. Chapter 30. Cosmological difficulties of Newton's theory. Apart from the difficulty discussed in section 21, there is a second fundamental difficulty attending classical celestial mechanics, which, to the best of my knowledge, was first discussed in detail by the astronomer Seeliger. If we ponder over the question as to how the universe, considered as a whole, is to be regarded, the first answer that suggests itself to us is surely this. As regards space and time, the universe is infinite. There are stars everywhere, so that the density of matter, although very variable in detail, is nevertheless, on the average, everywhere the same. In other words, however far we might travel through space, we should find everywhere an attenuated swarm of fixed stars of approximately the same kind and density. This view is not in harmony with the theory of Newton. The latter theory rather requires that the universe should have a kind of a center, in which the density of the stars is a maximum, and that as we proceed outwards from this center, the group density of the stars should diminish, until finally, at great distances, it is succeeded by an infinite region of emptiness. The stellar universe ought to be a finite island in the infinite ocean of space. Note, according to the theory of Newton, the number of lines of force which come from infinity and terminate in a mass m is proportional to the mass m. If, on the average, the mass density ρ is constant throughout the universe, then a sphere of volume v will enclose the average mass ρ v. Thus, the number of lines of force passing through the surface f of the sphere into its interior is proportional to ρ v. For unit area of the surface of the sphere, the number of lines of force which enters the sphere is thus proportional to ρ v divided by f, or ρ multiplied by r. Hence, the intensity of the field at the surface would ultimately become infinite with increasing radius r of the sphere, which is impossible. End of note. This conception is in itself not very satisfactory. It is still less satisfactory because it leads to the result that the light emitted by the stars and also individual stars of the stellar system are perpetually passing out into infinite space, never to return, and without ever again coming into interaction with other objects of nature. Such a finite material universe would be destined to become gradually but systematically impoverished. In order to escape this dilemma, Seeliger suggested a modification of Newton's law, in which he assumes that for great distances, the force of attraction between two masses diminishes more rapidly than would result from the inverse square law. In this way, it is possible for the mean density of matter to be constant everywhere, even to infinity, without infinitely large gravitational fields being produced. We thus free ourselves from the distasteful conception that the material universe ought to possess something of the nature of a center. Of course, we purchase our emancipation from the fundamental difficulties mentioned at the cost of a modification and complication of Newton's law, which has neither empirical nor theoretical foundation. We can imagine innumerable laws which would serve the same purpose, without our being able to state a reason why one of them is to be preferred to the other. For any of these laws would be founded just as little on more general theoretical principles as is the law of Newton.